the first law of geometric optics was the law of reflection, which I think makes good intuitive sense to us. The second law that pertains to geometric optics is the law of refraction, and that's a little trickier to get our heads around.
Shows up when we try to understand refraction. So we talked about the law of reflection last time. It applies when light travels from bounces off um, a material. Law of refraction has to do with what happened when light goes into a new material, say from air into glass. Um, and what happens is changing mediums bends the light, as we can see in our image of our fish tank here, right? So our fish is actually here, but as it hits that boundary between the glass, the water in the glass and the glass in the air, it bends, and it bends in ways that actually make it look like there are two fish there. So I'm sure you all have experienced such things. That's called refraction. And it results from the change of the speed of light in the different mediums. So the speed of light travels more quickly in generally mediums that are closer to vacuum. So gases, it'll travel faster in gases than it will in liquids and solids. And this is because of the way that light interacts with the atomic structure of different transparent materials. So we're going to have a good law of refraction, a good equation, but before we do that, we have to think about that difference of the speed of light. So we have to talk about the index of refraction, which is the ratio of the speed of light in a vacuum with the speed of light in a given medium. So what does that mean? Well, it means this number is always above 1, right? Because the speed of light can't travel faster than it does in a vacuum, right? So this is a maximum value. So this value is always going to be less than c, and that means this fraction is always going to be 1 or above. So you can see in gases, it's very close to 1. But when we look at liquids, there's a significant difference, right? So a diamond is it goes through a diamond, it goes about half the speed that it does through a vacuum, or less than that. So that's the index of refraction. And this is important to understand how the angle of the light changes as it goes through this change of medium. So why does the speed of the wave, the change in the speed of the wave, which is what happens here, why does it bend it? Well, this is a really hard question. We can think of it as the wave moving in at an angle and sort of one end of the wave being grabbed by the slower material. So here's our slower material. And so it sort of pulls the wave into a more perpendicular angle. Right here it comes at an angle that's very shallow, and then as it goes in this slower medium, it becomes closer to the normal normal vector there. That's always the case, right? As you go from the sidewalk here is faster, as you go from the faster medium to the slower medium, this angle is always going to be bigger than this angle here. So we can think of it that way. We can think of it as that, like this lawnmower example, when you go in the grass sort of grabs your tire, and as you push this, the mower naturally turns into a more perpendicular direction. But the truth is this is just a metaphor. There's nothing, the part of this wave here isn't connected to this in any physical way. It can't pull the wave that way. So recognize that we're just speaking in metaphors. This helps us remember that this angle is always bigger than this angle, but it's not actually what's happening physically. So what is happening physically? Well, this is where light starts to get sort of mind-blowing. But light travels from point A to point B in the shortest time period possible. So we can think of this as a lifeguard, right? A lifeguard, wants to catch this boat that's floating away. Well, he could run a straight path here, but he knows he swims a lot slower than he runs, right? So it's actually going to take him longer if he swims this way. So what he does is he runs up the beach almost to where he's parallel with the boat and then swims across to the boat. So in this case, the lifeguard's thinking, how am I going to get there faster? So what in the world is making Light know that this is going to be the faster path? And the answer is beyond our scope. Has to do with probability. It has to do with the fact that light is really both a photon and a wave, and it doesn't act as a ray. And it is really flabbergasting. It's one of the sort of amazing things about that wave-particle duality. But what we can say is that we know light is going to take that shortest path, and that's why light refracts. It's not being grabbed by the smaller or by the slower medium. So we have a law that governs the relationship between the incident angle and the outgoing angle here, and that is called Snell's law. And Snell's law is not too complicated. It has to do with the angles and the indexes of refraction. Okay. So this is, in this case, this value here is smaller, which means that this sine value is larger, which means that that angle is larger. Okay. So as this gets bigger, then this guy has to get smaller, which is why this angle is smaller in the slower medium. So like we said, light travels closer to the perpendicular direction when moving through the slower medium, right? So it comes in at a steep or a shallow angle here and leaves at a steeper angle. And it will follow the same path going one direction or the other, right? So this light could be shining in this way, or it could be shining in that way. And notice that those angles, this light here is parallel to this one because the same process is happening here as it did here. Snell's law is going to be the same there as it is there, no matter which direction light is traveling.